Good afternoon. Welcome to the course Thermodynamics of Materials. We are into lecture 185 and 186. So before I start, with the second case, T is 848 Kelvin, where we left off last class. Before we start actually the next class, before this only one correction is required. That is about the number, lecture number. The last class was only one lecture, namely 184. Okay, we are actually supposed to take two lectures, 184 and 185. But lecture 185 could not be held because of some noise outside. So we actually do one lectures. Okay, that is 184. So today it is 185 and 186. So now start with our discussion. That is resume our discussion. That is we are discussing system FeO and alternative stability diagram where log PCO is plotted against log PCO2. This is one, and the previously conventional one was actually example 3, and that was percentage CO versus T12. That is actually very popular, conventional, and this was the diagram, and we actually wanted to propose or wanted to draw an alternative diagram. This is the diagram actually. This is the diagram for 3 temperatures. This is the one. This is another one. That is T greater than 848 Kelvin. This is T is 848 Kelvin. This is T. This is actually T less than 848 Kelvin. These 3 cases we will consider, and we will actually always show the correspondence with this conventional curve. Okay, this is the one. So quickly, so this is actually we are discussing this. Second case, first case is already over. That is this diagram. This diagram here 4A was already fully discussed. In fact, we are actually we embarked upon the second one. That is T is 848 Kelvin, and we said that this was actually something that I wrote in figure 3. See, remember. 3 temperatures, once more concentrate. This is vertical line. From a conventional plot, this is the one temperature. This is T greater than 848 Kelvin. This discussion, the figure corresponding to this situation is here, even here, and it is all discussed. And today, this one, this vertical line, which is actually 848 Kelvin, this will be discussed. Or this we started discussing. Actually, we will complete this, and then we take up the last one, that is T less than 848 Kelvin, CC prime, that vertical line. So currently take up the BB prime line. So this I actually started what I wrote last day in figure 3 at triple point G. G is the triple point. Remember about triple point, you should note that it is not that 3 solid phases have met here. Here I have say triple point. 3 solid phases, namely FeO, Fe, and Fe3O4. This is not the definition of triple point. Okay, it may be possible, but not necessarily true, because when 2 condensed phases and 1 gas phase meet, that is also triple point. For example, water system. See, water solid, water liquid, and water vapor. That is a triple point. So that is, and also another thing is, it is not only 3 phases here. Actually, 4 phases. To be precise, 3 solid phases and gas phase. So it is not even 4 phases. Then what is the triple point? Definition where 3 equilibrium curve or stability curve. Repeat, 3, 1, 2, 3. 3 equilibrium curve meet, that is the triple point. Okay, so 3 curves meeting place of this. So that is at triple point G, and that is actually located on the vertical line BB prime, which is the temperature 848 Kelvin that I have mentioned. So G on vertical line BB prime, all 3 phases, Fe3O4, FeO, Fe, magnetite, wustite and iron coexist. This is corresponded in figure B. Corresponding figure is figure 4B here. This is 4A, 4B, 4C. 4B is this is the stability diagram for the system FeCO at T is 848 Kelvin. So what has happened here, I briefly described last class, that is yesterday actually. So you note this is these three lines in contrast to this figure where there are three lines separated, okay, separated from each other, A, B, C, D, E, F. These three lines have merged into one single line. And what it means actually, this is actually this stability for FeO, FeO, FeO3O4, FeO3O4. So FeO, FeO3O4, FeO3O4. These stabilities actually, the stability lines are merged into one. So I have written here lines A, B, C, D, E, F merged into one line. These compared to this, these three lines merged into one line. That's why you get a point here. Okay. Previously you had 3 points. One, the vertical line and intersecting with the curves. One, this stable curve, this is metastable curve, this stable curve. Anyway, 3 points. And so we had actually 3 lines. Here only 1 point. So we have actually one line marked into this. About this I said many things. Okay. This I will repeat is this. It is a quickest way or crudest way to understand this. What happens as this is T greater than 848 Kelvin. So this temperature and this is 848 Kelvin. So smaller than that. As temperature decreases from this to this, or say as the temperature decreases from this value. So suppose this is 900 Kelvin, say. So as decreases, say 890 or 880, such decreases for every temperature change, these 3 curves will keep descending. And suppose for example 880 Kelvin, then also you have these 3 curves. Only the separation between them will diminish. So why this happens actually, this decreases at greatest rate, at fastest rate. The line AB, the top one, here top one in figure 4A, it descends with temperature with temperature decrease at the descends at the fastest rate, and the second one at the CD at the intermediate rate, and the third one EF at the slowest rate. So what will happen? So as we decrease the temperature, there will be a temperature certainly when these 3 lines will merge into one line. That means what has happened? When the temperature is exactly 848 Kelvin, means this, then what happens? This has descended fastest rate of descent, it descends to this. And then the second one descends, which is actually moderate rate or say intermediate rate. So this descends to the same line. And the third, the slowest, descends to the same line. So this is this temperature. Again, if you further decrease, then again there will be separation, as you will see here. Obviously, so it will be very easy to follow. So then this I will discuss. Let me tell you what happens if you say, sir, further I decrease in this case, or the corresponding to this temperature less than 848 Kelvin. What will happen? So here they have marked. So this is fastest. So this will be the lowest curve. See, this is FeO equilibrium AB. See here, the lowest, fastest. So it is marked, it has been on par, then since fastest, it is the lowest. And the second, the middle one, that is Fe3O4. See, Fe3O4, CD is the in the middle of these 3 curves. Okay, so just above it. It is above it. Okay, and the slowest, which is marked here and which has not gone down too far, so it is on the topmost line. So this is the lowest one is the topmost line. FeO, Fe3O4. Very easy, very easy. In fact, you have got this. So this also in agreement with this figure also. This I will discuss. So since I will first finish this one, then we will actually take up the temperature of less than 848 Kelvin. So this is actually something that I want to discuss, but I will actually tell you. So let me complete this first of all. So I remove this correction you have already noted about the lecture number correction. So right. This is correspondent in figure 4b. Figure 4b dot next class, in student's class, by this is corresponding figure 4b by the superimposition of the three lines is A, B, C, D and E. A, B, C, D and E into one single line. See here, this is one single line into single line, along which what will happen? All phases are stable. Fe, FeO, they coexist. Fe, FeO, Fe3O4. Fe, Fe3O4 means all coexist here. As you see here also. Here all three phases. Fe, Fe3O4, Fe. This also means the same. So there is a correspondence between these two figures, okay? As it should be. So into one single along which all three phases coexist. So this is over. Second case B. Then let us take up this is all about this, okay? There is no metastable discussion. Metastable discussion will come back in the third case. The third case is what? T is even less. And that means this temperature, Cc prime, in this diagram, figure 3, conventional diagram, Cc prime, which is less than 848 Kelvin, and the corresponding diagram is figure 4c, this 4c, okay, this diagram. See here, interesting. We have two metastable lines. I tell you briefly, two dotted line means metastable, and one stable line. This I mentioned here. Which is stable here. See, as you see here, this temperature, see, it cuts which one? This is the Fe3O4 line. So the stable segment of Fe3O4. So we have Fe3O4 line means this one. CD line is actually now a stable line, and it has this vertical line intersected the metastable segment of this curve, FeO-Fe3O4 metastable segment. So it FeO-Fe3O4 equilibrium, FeO-Fe3O4 equilibrium, this one, top one, EF, is also metastable. Since this intersection metastable here, this is also metastable. And since this is intersected the metastable segment of the FeO right here. So FeO also a metastable line. So see, metastable, metastable. Between two metastable, one stable. Between two metastable, one stable. And which is that one stable is actually, this is the Fe3O4. As you clearly see, Fe3O4 carbon. You know this actually. So you have actually, you know this. Each stable part has its metastable counterpart. If you extend smoothly past the triple point, you will always get metastable. So for this, metastable is this GJ prime. For GH prime, smooth extension, and GF, what is this? GF prime. This T less than 48 Kelvin. So this discussion, and then we will actually also explain. I will explain in terms of, as I said, activity also, okay, and also say compatibility. They are not compatible. That part also I said. From this diagram you can get the answer, but that is kind of dependent type. You are dependent on this diagram. So suppose you want to be independently identify which is stable, which is metastable. I told you, actually metastable lines are always incompatible. This is one, okay. And another thing is this, from activity point of view, smaller activity is the line which corresponds to smaller activity is the stable line. The line which corresponds to the higher activity is the metastable line. This is the gospel truth. Because why? Activity means actual free energy, gives free energy. So activity, greater activity means greater free energy, and smaller activity means smaller free, gives free energy. So smaller gives free energy, phase will be the line which corresponds to smaller gives free energy will be the stable line. And the line which corresponds to greater free energy, higher free energy will be a metastable line. So this I said, I'll tell you here, okay. Because this is fine. So this T less than 848 K, let us have it. Figure 4C, right here, figure 4C shows the three parallel lines. Again, three parallel lines, remember same thing. Three parallel lines with slope of 1, already these are discussed. These lines are already drawn. Okay, they actually have shift. By the way, why they are shifting with temperature? You may ask. So why they are not fixed at one place? Why temperature changes, they descends? Who come on with temperature? What is different? What changes? Remember the equations? Just I just remind you one equation I am giving you. Log PCO, for example, I am showing you. Why slope 1? Remember, log PCO is log PCO2. I am taking one example, you will understand. Minus log, say second case, log KT and KT. 1, 2, or 3, etc. Okay. So what is the slope? Log PCO versus log PO2 plot. Slope is 1. And what is the other thing? What this gentleman is doing? This is the intercept. So slope remaining the same. Slope, slope. They merge into one with the same slope. And here also, they have actually spread into two metastable and into between which runs the stable one. Okay, this is a stable one. But in here, slope 1. These three lines also slope 1. What changes? Equilibrium constant. This is a function of temperature. So, you know, who governs? Which thermodynamic quantity governs the dependence of equilibrium constant with temperature. Remember that one, Van top equation, that is delta H 0, standard enthalpy change. So that data is given to you, known to you. So that accordingly they are descending, depending on their delta H 0, which are different. So at different rate they are descending. So no surprise. This is the meaning. This is the thermodynamic reason, explanation. Okay. So remember slope. Shows the three lines. Slope unchanged. Slope unchanged. These lines are already drawn. Okay. Shows the three lines. Shows the three parallel lines. Sorry, three parallel lines. See again parallel. 1, 2, 3. Again slope 1. Three parallel lines. And each of slope 1 comma, okay, AB, what is the name of this? AB here, see, read this curve now, because this curve is under discussion. C, 4C, this curve, corresponding to this vertical line, CC prime, this temperature, no more. So this is the original, not original, this is the one type of diagram, very popular, very useful, conventional, no doubt. But this is an alternative attempt. Okay, anyway, this CC prime, this temperature concentrate, which is less than 848 Kelvin, and corresponding stability diagram with log PCO versus log PCO to plot, instead of percentage CO versus T plot, is this one, this figure. What is this about? Remember, here two dotted line, topmost and bottommost. The intermediate line is stable line, which is meant for the equilibrium of Fe-Fe3O4. Okay, means this curve. This is Fe-Fe3O4. So this is the stable line, and other is topmost is FeO-Fe3O4. Okay, as I explained you actually, this FeO-Fe3O4 is this one. It has actually gone to this FeO line, for example, which is the bottommost FeO line, because it is the fastest speed. It is descending, so it goes to the bottom. Okay, merged and then goes to the bottom, FeO. Okay, and then middle explain, and then the lowest one, which is the slowest one, having slowest rate of descent, then that will be on the top, FeO-Fe3O4. By the way, the topmost and the bottommost, top and the bottom line, two lines, are metastable lines. Here also, metastable. Between two metastable lies the stable. Which is Fe-Fe3O4. And means this is also Fe-Fe3O4. So let us write down two things. Okay, B, which AB and EF are AB, CD and EF, of which CD is the stable curve. Remember, these things have changed. Has been totally opposite, reversed. See, here CD was the metastable. Here CD is the metastable. CD is the stable. And here AB and EF were stable, and here AB and EF are metastable. Okay, so of which CD is the stable line. Remember, when I talk about CD, AB, they are stable lines. They are not stable phases. Stable lines. Okay, so because stable line, metastable line. Okay, and phases are for stable line, metastable, stable, metastable, stable, metastable, and these are the phases. FeO, etc. And along any curve, two phases, two condensed phases, namely, for example, here Fe, FeO solid are stable, means coexist. Together stable means along the line, but above the line Fe stable, below the line FeO stable. This is the okay. And remember, when I say two condensed phase coexist, means along with the gas phase, because see y-axis what is you are seeing, let's see percentage CO. CD is the stable line while let me finish this, while AB and EF are metastable. Are the metastable lines. Stable lines. Okay. Again say the correspondence. This stable line corresponds to which line here? For example, this stable line this CD corresponds to GJ. This is a stable curve GJ, and indicating the equilibrium between Fe and FeO4. So this is the correspondence. And similarly, EF corresponds to FeO means here GH prime curve. Okay, the metastable one, and this metastable AB FeFeO. What is the this is stable part? This is the metastable GF prime, etc. So that is this. So while the stable line CD, the correspondence with this curve, with the conventional curve, this stable line CD corresponds to the stable curve GJ. Repeat, GJ, figure 3 or figure 3. While the metastable lines namely which are the AB, see AB and EF, the topmost and bottommost. Okay.
Lecture 185, 186 not visible.
Okay.
Everything else okay.
Okay. While the metastable lines AB and EF correspond to the metastable curves as I have already said. These two occur is metastable curves GF prime. AB means AB is what? FeFeO. And what is the FeFeO metastable? This one. This is FeFeO. This GF stable metastable is what? GF prime. This is F. This is F prime metastable. GF prime. Easy to remember. GF prime. GH prime. GJ stable. GJ prime metastable. So metastable curves GF prime and GH prime respectively. Figure 3. This is in conformity with the vertical line CC prime. CC prime of figure 3. How it is in conformity, how it is in agreement. This says the next line, next couple of lines will tell what? If you see this figure and this figure, if you increase the percentage CO according to figure 3, or PCO, log PCO, means PCO, if you increase the PCO, the sequence of reduction is what? See the sequence, start with Fe3O4, go this way, sequence is what? This vertical line follow this, it is Fe3O4, then it converts into what phase? Fe. And here also you see, if you see these are metastables, ignore, this is a stable, Fe3O4 into Fe. That means in both cases it is Fe3O4 directly to Fe, means no intermediate formation of FeO. Very interesting. This happens when the temperature is below 848 Kelvin. This is very well known to metallurgists, that FeO will not be formed below 848 Kelvin. But if it was above 848 Kelvin, what is the sequence? Fe3O4, then FeO, then Fe. Covering everyone. Fe3O4, FeO, Fe. And if you started with Fe2O3, means if you added that line, Fe2O3 stability line, which I have actually omitted for simplicity, then it will be what? Fe2O3, Fe3O4, FeO, Fe, if the temperature is greater than 848 Kelvin. Say 900 Kelvin, 10,000 Kelvin, 1100 Kelvin. So this. And if it is less than, once more, I repeat, suppose you started with Fe2O3 to Fe3O4, no problem. Then Fe3O4 diagonally jumps into Fe. This according to this figure as well as this figure. So this is actually, so with the vertical. So this is in conformity with the vertical line CC prime of figure 3. Here, what is the conformity? You give a star here and remove this. Second point is over, so we can remove this. And this, so we'll complete C also very soon. That's nice. Okay, I have got some space to write and no problem. Now it's okay. Start from here. Okay. So continue. How it is in conformity? Explain. So here. Continue here. Huh? So for example, as percentage CO in that is according to figure 3, or PCO, means log PCO actually, or PCO figure 4C, increases the sequence of stability is what? That means sequence is what? Fe3O4 to Fe. And this sequence I wrote in the first case. Here, what I wrote here? That exact language I used, exact sentence. The sequence is Fe3O4 to this is metastable. Ignore Fe3O4 to this is both in agreement. FeO, Fe3O4 to FeO to Fe. And this side also Fe3O4 to FeO to Fe. At first case, that is greater than, any temperature greater than 848 Kelvin. So the sequence of stability is just Fe3O4 to Fe. Fe3O4 to Fe, okay. Bypass, I once more repeat this. Actually, I'll mention at the end that if hematite was present, Fe2O3 was present, Fe2O3, I write at the end Fe2O3 to Fe3O4, that part will be unaffected. But Fe3O4 to Fe, no way to accommodate FeO. No. See, clearly see FeO, see the stability field of FeO collapses here. See this see the two points, okay, see these two branches, and here within which sits the FeO stability field, and it ends here, namely 848 Kelvin. This is actually is 675 degrees centigrade. Let me think about this. Yeah, no, I'm sorry, 575 degrees centigrade. See, 575 degrees centigrade. Okay, this is well known temperature. Very well known. That's below 575 degree centigrade. FeO is unstable, metastable relative to Fe3O4 and Fe. This is actually known, this diagram. Okay, this is well known. So the sequence of stability is Fe3O4 to Fe. To continue this, bypassing the formation of intermediate solid FeO. Intermediate solid FeO. So this is actually our, this establishes this is the fact that FeO solid is unstable below 848 Kelvin. Below 848 Kelvin, and the reduction of this discussion is actually relevant to what? Blast furnace iron making, particularly in the upper stack zone, stack. See this reduction sequence observe. So if the temperature is greater than 848 Kelvin, or say sponge iron making, okay, or say direct reduction of iron oxide, okay. And so this discussion is relevant, and you have actually perhaps used this stability diagram often in connection with those processes, and the reduction of, so what I mentioned here, FeO solid is unstable below 848 Kelvin, and the reduction of Fe3O4, or for that matter Fe2O3, because you will be satisfied if Fe2O3 is included, because starting oxide is hematite, Fe2O3. So Fe2O3 also, that diagram I have not considered. I at the very beginning I declared that for simplicity I have ignored that one, but that can be included anytime. So Fe2O3. So Fe2O3 is okay, or the reduction of Fe3 and the reduction of Fe3O4 or Fe2O3 if it is to iron, no problem, to iron by CO-CO2 mixtures, okay, by CO-CO2 CO2 mixtures. This percentage CO means you know very well, percent CO in the CO2 mixture. So by CO2 mixtures won't involve a FeO solid as an intermediate product. As an intermediate product. Intermediate product at mentioned about the temperature, at temperature is less than 848 Kelvin. Okay, that is the famous 575 degrees centigrade. There it ends. Okay. So remember, I repeat, what is the sequence? Suppose you started with Fe2O3, what will be the sequence? At T greater than 848 Kelvin, once more, Fe2O3, suppose this line, suppose there is a line here, okay, I told you. You ask me, I can draw this line, okay. Since it is, I have almost ended. So what is this? What is table here? Fe2O3, I told you this is very small region, okay. He almost marked it with x-axis, okay. But anyhow, the same it is there, okay. Fe2O3 exists. So Fe2O3, then I'm again talking of greater than 848 Kelvin. Fe2O3, then Fe3O4. So here, start. Fe2O3, Fe3O4, FeO, Fe. As we know, that is the sequence. But if the temperature comes to less than 848 Kelvin, is considered as less than 848 Kelvin, then what it is? Fe2O3, then Fe3O4, then Fe. No FeO. This is the sequence. Okay, this careful about this. But another thing I have to, for the sake of completeness, I have also mentioned here, to identify without taking help of this conventional diagram or referencing this conventional diagram, use independently decide whether which is stable line, which is metastable line, which are metastable lines, which is stable line, etc., etc. For example, I tell you, I have written here, follow, compare these two gentlemen. You know the answer. You know this is the line, CD is the stable line, and EF is the metastable line. And we remember I always that I am talking of T less than 848 Kelvin, figure 4C. So, see, which is, what is the activity of Fe3O4? I compare the activity of Fe3O4 as obtained from this line EF and as obtained from the line CD. Currently, as if I don't know which is stable, which is metastable. We'll figure out. We'll reason out. Repeat. So you tell me what is the activity of Fe3O4. First you take up EF. According to line EF, what is the activity of Fe3O4 here in this domain? See, it is said what Fe3O4 is stable. See, along the line FeO and Fe3O4 both coexist. Below the line Fe3O4 exists means activity, physically present, means activity of Fe3O4 is 1 below the line, EF, over, answer obtained. Then you asked CD, the line CD, what is the same region, same location, what is the activity of Fe3O4 according to this line, to you means to the line CD. CDC, read the equilibrium, it is Fe3O4. Above the line Fe stable, below the line Fe3O4 stable. So below is how much? Below means it is physically present and activity is 1. But above the line, it is not physically present. Fe is present. So activity of Fe3O4 according to the line CD is, since not present physically, less than 1. I have written here. See here, you see there, activity of Fe3O4 less than 1. This is less than 1, this is 1. Which is lower? The activity result obtained from line CD. Hence CD is the stable line. and EF is not stable line. Activity or free energy gives free energy. Activity less means free energy less, and smaller free energy, lower free energy or smaller free energy will be the stable state. So stable refers to the stable state. So here I will say this, that means this is the stable line. We are trying to identify whether CD is stable line or EF is stable line. So resolve is CD is stable, EF is not. Then again compare with AB. Finish this discussion. CD and E. What you will consider here? Again, see, I have taken up iron because that will be convenient. So you tell me again, according to CD, what is the activity of iron? Tell me. Above the line, iron physically present. Below the line, Fe3O4 is physically present. Iron is not. So what is the activity of Fe below this line? Means this region that is below the line CD and above the line Fe. That is the region, common region. And ask both of the lines, both the candidates, what is the activity of, say, iron here. Chosen species is iron. So iron. So CD first CD. What is the activity according to you? Answer is, since here Fe is stable above, not below, so activity of Fe is less than 1. Very good. Save this result. Take up line AB and it says what? See, this is Fe-FeO equilibrium. So above the line Fe and below the line FeO. So above the line means this same domain. Who is stable? Fe is stable. Then what is the activity physically present? Means activity of Fe is 1. Activity of Fe is 1 I have written. And so 1 says, line CD says, according to it, says activity of Fe is less than 1. At the same location, according to line AB, activity of Fe is 1. Which is lower? Less than 1 is lower, means, and this lower value, the line which refers to the smaller value of activity is the stable line. So CD is again the stable line, AB is metastable line. So you see, CD is the only stable line and both are metastable, these two lines. Here also, as I already said, this point, the vertical line intersects here, here, here. Here this, it is metastable. Here metastable means we get metastable. Here and here metastable. So two metastable, between two metastable lies the stable. Between two metastable lies the stable. So I think I have discussed enough. So with this we have completed this topic. I'm sorry, this topic right there, subtopic rather, construction of stability diagram, 6 examples. See, 6 examples. This is the 4th example running, and now it ends here. Here it ends. Okay. So this stops here. Okay. We will just remove 1 line or 2 lines. So with this we have completed 4 problems so far. 5th problem we will take up now. 5th. Let me remove this many figures. So I will remove this 4. This is pertaining to 1, 2, 3, 4. These 4 figures I am removing, and this right there. Only this figure will remain. Figure 5. That is the 5th example, and I will give the title of the 5th example. So I keep on, just I remove this. Start removing the caption itself. The broad capsule still remains. Construction of stability diagrams. So let me remove first this one. This one. Then you take up, remove this figure. You will remove this figure and this figure also. Okay. So let us bring the board first, then we will let's remove this also. Remove this figure also. So I will take few moments. Figure 4C caption out. Careful, don't damage this. This is actually, this line is okay. It's okay. It looks okay. Well, how much time?
52 minutes gone.
50?
52 minutes gone.
So 48 minutes means okay.
1 hour 8 minutes left.
And 1 hour 8 minutes?
Right.
Great. Okay. So it will be roughly 6:30. Okay, thank you. Thank you. Thank you. So we are about to start. The topic is actually, I tell you, it is iron, manganese, oxygen stability diagram. But here we have, actually this has reference to, I would say, steel making. You blow oxygen into metal phase and you have FeO formation and manganese, FeO and MnO formations. And even in equilibrium with the metal phase, slag phase and metal phase. So it has some connection with that. So, but anyway, we will actually consider, that is the practical aspect, but we will consider that FeO-MnO system. What system? Right, this is the diagram. This is the diagram that will, yes, actually you see, stability diagram for the, I tell you what, let us write. Example 5, okay, take example, system FeO-MnO involving FeMn. This time we are not dealing with pure phases. impure. The solution phase. A mixture of solution, two solutions separate. One is metal phase, metal solution, another is oxide solution. This oxide solution is actually in the language of metallurgists is slag, metal slag equilibrium, involving FeO-Mn, metal phase, slag metal equilibrium is a common phase, a slag metal gas. If you want to incorporate everything, but slag metal equilibrium very common. FeO-Mn metal phase and FeO-MnO. This is a caption I am writing, and FeO-MnO oxide. Oxide, writing here, oxide phase. Let me write. Actually, it is better I write here, na? Oxide phase involving oxide phase. Both ideal solution. For simplicity, we have considered metal phase is an ideal solution, ideal solution, Raoult's law. And oxide phase is also ideal solution. So both ideal solution and what else? And immiscible. And immiscible with each other. With each other means slag metal will not mix. You know this actually. That's why that is how we are. That's why we prepare slag and we remove slag. Okay, tap metal and we also remove the slag. Okay, so this is drain out the slag. So they are immiscible. So they don't mix up between themselves, but by itself they are actually solution phase. Metal is a solution of iron and manganese, and oxide phase is a solution of FeO and MnO. Okay, so with each other, and the gas phase, which is oxygen. You know, gas with oxygen. This connection is this in LED steel making or OBN. You blow oxygen. So oxygen gas. Oxygen. Okay, that's it. This is the oxygen. This is the topic. This is the topic. So this is, what is this? I actually construction of stability diagram, give a underline here to give a demarcation. So this is the system FeO-MnO involving FeO-Mn metal phase and FeO-MnO oxide phase. Bracket. Both ideal solution, both being ideal solution and immiscible with each other, and the gas phase. So three phase. This is the diagram. This is the stability diagram. I repeat this. This is the stability diagram. This is answer to the question. What is draw the system construction of stability diagram? This is the iron, manganese, oxygen. What is the figure 5? Stability diagram for the system FeO-MnO showing the stability fields of metal phase FeO-Mn. What is that? This one, this metal phase. Oxide phase. What is that? FeO-MnO. What is there? Here. Sorry, sir. Careful. Oxide phase here. Oxide here. Above these two lines and one below the line. Metal phase below the line. Oxide phase, and between the two, enclosed within the curve is the metal plus oxide mixture. And metal oxide And what I have written? And metal plus oxide, this is plus. Metal plus oxide mixtures. So these phases are shown in the diagram at a given temperature. T is fixed. These all explanation I will give you starting from the very beginning of the phase rule. That every time I do that. To begin with the phase rule. How many variables have a minimum number, maximum number of degree of freedom, okay, minimum number of phases involved. So that way I will try. But this is the diagram. I tell you, this diagram I first came across in the book of King. I will give right here in the book of Kingery, famous book, Introduction to Ceramics. Name is Introduction W.D. I am writing the full name. You know very well. Introduction to Ceramics. Remember, but in that figure, this discussion that we will make here, that is equations for these curves. This curve, lower curve is named ABC, metal curve. The upper curve is known ADC, oxide curve. What are the equations? That is the very important question. How do you get this curve? Is it quantified? Okay, it is quantitative. So what is the equation? Involving thermodynamic parameters, data. So that are not available. The equations are not available, which we will do, and no phase rule analysis also. That we will take up. So remember, but I give the reference I am writing, but only for the figure. And maybe some discussion I don't exactly remember, but I remember that these equations are not developed. The equations for ABC and ADC are not developed, and no phase rule discussion. Okay, that is detailed phase rule discussion not there. So you may look at the book, so I give the reference so it helps you. I am writing here, it is better. Right, reference W for the figure only. Means not beyond. For the figure only is what is reference, right? Introduction, I'm sorry. But anyway, Introduction to Ceramics. The name of the book by W.D. Kingery. A famous name, a very famous name indeed. And also I should admit humbly that I was benefited from the diagram. Only diagram given, I got a clue. I got an outline, or I know the answer at least. So I developed the whole thing, thermodynamic development, equations for these curves, which I do now, and phase rule analysis. So it is a part of our construction of stability diagram exercise, as an exercise for the construction of stability diagram, and also, as I say, it is actually stability diagram, and okay, this is also an application of the phase rule. Okay, involvement of the phase rule gives phase rule. So start. So this is the, in nutshell, this is what I said. This is your introduction. Oh, by the way, what is plotted here? See, FeO2 versus XMn. On the x-axis, see, 0 to 1 means iron. This side, that side is Mn. And the top x-axis also XMnO. XMnO, manganese oxide. In this mixture, when you refer to this x-axis for this oxide phase, and for the metal phase, refer to this x-axis. Here also 0 to 1, FeO, this side, and that side is Mn. Okay, and FeO2, this is the one. The name of this curve is what? Okay, ABC, and the upper one is ADC. Okay, and remember, I'll mention that these two curves are interdependent. If you find this point, this will be automatically this point in this curve. Suppose you are drawing this curve, means you will be able to draw this curve. Why? How? Suppose one example here. you get this point here, the other point will be what actually? This one mathematically, this point. So similarly, this point, this point, this point, this point. You connect these points, or say this point, this point, this point, this point. Connect the points, you get the curve. So no problem. This also I mentioned. Now let us move on. To begin with, as I do, to begin with, as before, a max. This is a planning about drawing the diagram. How many variables I have to handle? I want a 2-dimensional diagram, not 3-dimensional. So a max is C minus P mean plus 2. What are there? C is 3, P minimum is 2 plus 2. Why? Explain this. C is 3 how? What are these? Iron, manganese, oxygen system. C is 3. P minimum is what? What is C? Minimum number of phases. You have a metal phase plus oxide phase here. Two phase and gas phase always on the y-axis. But below is only metal phase. So minimum is, and above is also only oxide phase. So minimum number of phases actually that I have to handle is 1, not 2. 1, okay, I'm sorry. 1 in either metal or oxide, minimum, plus gas phase. So 2. So I've been here. P minimum is 2. What is this? 1 condensed phase. Can I write? 1 condensed, we say condensed, okay, when it is liquid or solid, condensed phase. 1 condensed phase plus 1 gas phase. Remember, I repeat this. Never ever forget, this is stability diagram, this is equilibrium diagram. Okay. So equilibrium constant will be coming into picture, all such things, okay. So what is this value? Value is 3. Then what you do? Fix 1, 3. Fix 1, plot 2. This is the deal. Plot 2. Fix 1. What you will fix? Temperature. See, T is fixed. Your chosen temperature. So 1400 degrees centigrade, 1600 degrees centigrade, etc. 1873 Kelvin. Plot 2. What you will plot? See, XMN versus PO2. Well, write this PO2 versus same thing, go XMN, or as I have already told, XMN and XMN are dependent on each other, so interdependent. Or you can write PO2 OO or PO2 versus XMNO. Okay, PO2 versus what is this? For to arrive at the for metal curve. One you do, other will be automatically for metal curve. This is for oxide curve. What is the metal curve? This one, ABC. What is the oxide curve? ADC. Okay. So this actually, or this, you give a bracket here. Plot 2, this the 2, plot 2, okay. Note here, take a note. X7 and, as I told you, and XMNO are mutually dependent. Mutually dependent. You will get the relations there. They are mutually dependent. Okay. When XMN is here, XMN is there. As I have shown with the help of one example by dotted line, I have shown this. Good. Let's begin with this. Okay. This is all construction of the diagram. Let us start. Okay. Consider the following simultaneous equilibrium. You just consider the following two simultaneous equilibria. Who are there? Fe liquid underscore means impure plus half O2 gas is FeO again underscore oxide FeO liquid. This liquid is oxide phase and this liquid is metal phase. Okay, and they are separate. Okay, they are not miscible. Okay, they are separated. Okay, so anyway, they are each actually is a solution. It is a solution of iron manganese, this liquid, and this liquid is a solution of FeO and MnO. So what is the next one? Quality equation 1. What is the next one? Similarly, Mn liquid plus half O2 gas is MnO liquid. Quality equation 2. Okay, very good. Now start delta G01 as you do always is A plus Bt. No doubt about this, and A and B are known quantities. Get a book, standard state. Okay, A plus Bt is what? Minus RT ln KT 1. This leads to, since T is fixed means you know the T. Suppose 1600 degrees centigrade, suppose 1550 degrees centigrade, corresponding Kelvin. 1600 degrees centigrade means 1873 Kelvin, etc. etc. So fixed, you know. So this allows you to know KT1 is a known quantity. If it is known quantity, then write the expression AFeO by AFeO. What is you write here? Oxide. Mention. And the oxide liquid. Liquid, remember, both are liquid, molten state. And by AFe. This is metal. This oxide, I am saying oxide, but actually in our in industry, in plants, or in our study, or the steel making study, we say slag. We call the term slag. This is slag, this is metal, slag metal. And you have written this oxide, and then what you have? PO2 power half. Now tell me what it is. Tell me what it is. Activity is what? This phase, this activity of FeO is what? Ideal solution. So what is the activity? Raoult's law. Activity is mole fraction. So write this X FeO and write activity of, this is also ideal solution. X Fe PO2 power half. You write for ideal solution. We know AI is Xi. No problem. Okay. I think you are right here. You have to give a level and equation number 1, 2, 3. Okay. Take up the next one. Similarly, right. Similarly, right. Delta G0 to A plus Bt again. Known quantities which are different though, which are different values, but known is minus RT ln KT2 leads to KT2 being known is the expression for this is what, right? Nicely, activity of MnO oxide liquid oxide, okay, MnO by Amn is the metal and PO2 power half. Again you write similar, this is XMnO since ideal solution, and this is XMn PO2 power half. PO2 power half, okay, very good. Call it equation 4. This is 3, this is 4, okay. Very good. Now from 3, continue. I will write here, right? From 3, what you get? XFeO is what? Right? What you get? XFeO is, right, nicely, KT1 times XFe times PO2 power half. No doubt, okay. Now I am doing one thing. I want to, since XMn I have shown on the x-axis, I need an equation. See what I am doing, what I am trying to arrive at, what I am trying to get to. Now equation involving PO2 and XMn pertaining to the curve ABC and for the curve ADC separately. This is the objective. Once the equation obtained, then draw the curve and stability diagram over construction of stability diagram. Then apply. Application is also requires your concept. What I am writing, since I actually want to express in terms of XMn, so what I will write? KT1 times 1 minus XMn PO2 power half from 3, from 4, complete this here, so careful, from 4, similarly you tell me from 4 what you write? XMnO, right, KT2 times XMn times PO2 power half. Okay. What is XMnO? By the way, I am trying to relate that is 1 minus XFeO, because binary, this is binary solution, oxide, FeO-MnO, binary. So they together is 1, mole fraction together 1. Similarly here XFe, I have written here already. XFe is what? 1 minus XMn, because XFe plus XMn is right here. Since XFe plus XMn is 1, I am writing. And similarly here I am writing XFeO plus XMnO, where it is XMnO is 1 minus XFe, because they together is 1, so 1 minus XFeO. Then what I am trying to do, I am trying to substitute these values, XFeO values. What is this? Write the value of XFeO from here. KT1 1 minus XMn PO2 power half. Happy? Okay. So what you are getting? Like that. Okay. This simplify 1 minus KT1. First term is PO2 power half, and next term is plus KT1 XMn PO2 power half. So this and this you are getting, okay. So you are getting XMn PO2 power half, XMn PO2 power half. Get them together. If you get them together, or I may write here very easily, okay. So I am writing is what? I take this to this side, okay. This to this side, okay. Okay. I am writing this to this side. What do I get? Let me write this. KT2, I will tell, let me take common XMn xmn PO2 power half to the left hand side. To the left hand, here it is also present. This is what KT2 minus KT1. This comes to this side is what 1 minus KT1 PO2 power half. Or xmn is what? You are very close. xmn is what? Please let me write you. Right? 1 minus KT1 PO2 powered half over xmn PO2 powered half times KT2 minus KT1. Just let me check. Let me check. Huh? Let me check. It is okay. 1 minus KT1 PO2 power half. KT2 minus KT1 x7. What I did? Okay. Have you not noted? xmn is there. I'm trying to write. So why xmn will come here? Unnecessary. xmn is here. So PO2 power half. It's okay. Over PO2 power is correct. Absolutely correct. So simplify this. I am simplifying this. This is the last line maybe. Or xmn is right nicely. The last line. 1 by, I divide by PO2 power half. Numerator and denominator. PO2 powered half minus KT1 and retain KT2 minus KT1. This is x7 versus PO2 relation. This curve, ABC curve. Is x7? This is what mean for this middle curve, and x7 mean for the upper curve, oxide curve. So can I, since this is the final form, you all set? This is the relation. I think you don't have any problem here. KT2, this is KT2 clear. Make no mistake. Okay. You will not get this relationship in any book. This work in any book on earth. Okay. This you will see. So you can check this. Okay. So this is experiment. So this, so shall I give what? Star. I remove from where? To begin with, as before, I don't need this. This thing I don't need anymore. I don't need anymore. I don't need anymore. Just clean this place. Star, star, So what you see, I tell you what. You see, if PO2 increases, if PO2 increases, follow this curve ABC. This is the equation for the curve ABC. If PO2 increases, then Xmn is what? It increases means whole thing decreases. So Xmn decreases. Take a look. Follow this curve. When PO2 increases, Xmn decreases. So consistent with the diagram. So let us write this out. So this is the first of all mention that this is the this Xmn versus PO2 relation, this Xmn versus PO2 relation is the what we will give a name to this. I'm not giving any name. I see Xmn versus PO2 relation is the what? Is the equation for the curve, metal curve ABC. This is what is the metal curve ABC is the equation for the metal curve C ABC A B C metal curve. Okay, Xmn versus PO2. Okay, remember Xmn applies this curve for the Xmn is suitable, appropriate, and for this curve XMNO is appropriate. Curve ABC, again ABC. Note as see here from here as PO2 as I said PO2 increases, what happens? Whole thing decreases, so Xmn decreases, which you see also as PO2 increases, PO2 increases, Xmn decreases. So consistent with the, in conformity with this figure 5. So in conformity with figure 5. Mathematically as well as figure, in conformity. What happens? With figure 5. So you have drawn the curve. When you have got the equation, you can draw the curve. How you might ask, sir, KT1, KT2. Already I have shown you here. KT1 from delta G01, data book, and KT2 delta G02. No problem. With a simple calculator, you can draw this. Okay? You don't need any programming. Okay? This part is all. What is remaining? This curve is addressed ADC. What is the equation? This is XMNO versus PO2. How will you get that? For this, hook upon this one. This will be very nice. Now, from this. Now, I believe this you will use this. XMNO. Next is XMNO is, let me write, KT2 PO2 power half times XMN, this one. Substitute XMN and the answer. substitute XMN. This will be your answer. So KT2, let me check, just it in the right path, KT2 P to power half XMN. Okay, write that. KT2 is okay, Bapu? Everything okay? Okay. I hope.
Half an hour left.
Okay, thank you. 82 times, okay, Q to power half, and XMN, this whole thing, write nicely. Remove this, remove this, remove this. Write this expression, KT2 minus KT1 in the numerator, 1 by PO2 power half minus KT1. That's it. That's it. Or you want to simplify a little bit perhaps? Oh, this is, okay, I remove this line also. These two lines. A little bit simplification is possible. Why? You write KT2 keep here and you include PO2 here. So it is 1 minus okay, wait. Tidy up. Multiply this. Multiply by this the numerator. KT2 PO2 cancel minus KT2 times KT1 PO2 power half right here, or XMNO. It is better right here. XMNO, it is better, equals to, give a line this KT2 minus KT1, okay, divided by KT2 minus KT1. Let me check for the last time if it's okay. KT2 minus KT2 KT1 PO2 power half and KT2 minus KT1. That's it. Box. A box here. This is, right, this is XMNO versus PO2 relation. This is relation. Actually, write this way. This XMNO versus PO2 relation like this is the equation for the which curve you say? Oxide curve. Upper curve is the oxide. Remove this. This is right here. This for the oxide curve. Oh, I don't know why this is. For the oxide curve, what is the name of this curve? ADC. For the oxide curve, ADC. Again, note as before, as PO2 increases, like here, PO2 increases means minus, means decreases. XMNO decreases. PO2 increases. What happens here? PO2 increases and with negative sign, there is a negative sign here. So decreases. Whole thing decreases. XMNO decreases. See here, see, concentrate this curve, ADC. PO2 increases, PO2 increases, it's PO2. Increases, XMNO decreases. So in conformity like this, in conformity with figure 5. It ends. Only thing, one comment I will make about the shape of the diagram. Do you see anything? Something familiar? You have come across number of times? Looks like binary isomorphous diagram. Binary means where liquid solution, binary system AB, where actually both liquid solution and solid solution are complete liquid solution and complete solid solution, complete range of solid solution and complete liquid solution, or complete solubility between A and B in liquid state as well as solid state. Binary phase diagram we call isomorphous system. Okay, so that diagram looks like this. So look, apparently it is interesting. There is no connection, because that is actually, this is actually what happens here. There, one is solid solution, another is liquid solution. This is both are liquid solution. Yeah, oxide liquid, slag, metal liquid, no connection. And moreover, what is plotted? PO2 against XMN. XMN may be admitted. PO2, what you plot there? Binary isomorphous system. What you plot? Temperature versus XD. It is PO2 versus XMN. And here temperature, that temperature is a variable. Here temperature is fixed. So no connection. Only shape, strange enough, similar. So it is interesting. Note that figure 5 has the same look as a binary isomorphous system. Binary isomorphous phase diagram. Binary, and there it ends. Example 5 is over. All over. So I'll take up next example 6. System. This is actually, when we introduce, I don't know how long actually it will be possible, but let us start. Last example. 6th example, 6th next. So this is over. This is all over. Okay. So system is lead tin oxygen. I remove this, I must remove this. This headline is over. System, I remove this. line as well as the lower lines, some of the lower lines. System. What is the last example? System lead tin. And let me change the pen. Okay. Lead, tin, oxygen. This is the last example. What is involving? Let me write. Involving. What is involved? Lead, tin, liquid alloy, liquid solution. But this time we consider this is not ideal solution, non-ideal. So lead, tin, non-ideal, liquid solution, involving this, then lead oxide solid. Unlike this, here oxides are in solution, two oxides are in solution. This time oxides are pure. Metals in solution, lead, tin, metallic solution, liquid solution. But oxides are solid and they are immiscible, pure solids. So what are the corresponding oxide? PbO. And from SnO2. So these are pure solids. So but here it was actually impure. This is FeO-MnO is a solution, liquid though, but solution. But so the solution involving right here PbO solid, and then the other oxide is SnO2 solid, and the gas phase. Again gas phase. Which is oxygen. This is the topic. I remove this. I remove these lines. Okay. Again, to begin with, as you do, I tell you what, some introduction. We will draw the stability diagram like this. Different type, but stability diagram. For lead, tin, oxygen, we draw the stability diagram, equilibrium diagram. And one important conclusion, inference, we will make from that: what is the maximum extent of tin removal? What is the maximum extent of removal of tin from lead? This you try to find out. This is additional exercise. Why? This is actually relevant in where? Softening of lead. Softening of lead by controlled oxidation. So oxygen gas phase. Control. So softening means how lead is softened by removing tin from it. So in that connection, this diagram will be very helpful for understanding. So removal of tin from lead tin alloy by oxidation or control oxidation. To begin with, as before, M max is what? C minus P mean plus 2. What is that value? C is 3 component system and 2 again 2, because okay, this I will show you actually. Say suppose one minimum condensed phase will be present. Okay, so let's say lead tin, say, so condensed phase, liquid solution 1, and gas phase always present 2. Or if you consider PbO solid, that is also condensed phase 1 plus gas phase. Okay, anyway, so minimum, the least number of phases, P minimum is 2 plus 2. Explain here, C is 3 how? Here lead, I have already written, but you write here once more. This is the C is 3 explanation, and what is the P minimum is 2, because 1 condensed phase plus 1 gas phase containing oxygen. So gas phase, and this whole is, so giving you how many? Minimum phase 2, component 3 is 3. If it is 3, then 3, you have to fix 1. You have to fix 1 and plot 2. Then it will be 2-dimensional. So fix 1. Fix 1 as we did here. It was 3 here also. Fix 1, temperature, plot 2. Plot 2, fix 1. Here the same. Fix 1, plot 2. What is the fix 1? We will consider temperature again. Fixed temperature. So I will draw the diagram. We'll consider for given temperature. T is fixed. What is the plot 2? Plot 2 will be what you know. Again, PO2 versus, like PO2 versus here, like here, not this, but there PO2 versus XSN. XSN in the liquid solution, non-ideal liquid solution. This will be the variable that you will consider. Fix 2, plot 2. Okay, this is the construction of the diagram. Next is construction of the diagram. Construction of the diagram. Consider the following two. Remove this. Consider the following two like this. Consider the following two. Simultaneous equilibria. What are they? You can write like last time. So consider PB liquid plus alloy. This is impure alloy plus half O2 gas. Carefully, it is liquid solution, means lead tin alloy. So lead, I consider lead, but impure lead. So half O2 gas goes to what it will form? PbO solid. And then other one is call it equation 1. Then Sn, again impure, in lead tin alloy, plus O2 gas is SnO2 solid. Equation 2. Okay, happy? So can I remove this now? Remove this. These are all over, unnecessary. So remove this. Okay, very good. Start. Putting. So just let me clean up this one. Mess. So delta G01 as before. Delta G01 is what? A plus BT, where A and B are known quantities, is minus RT ln KT1. This gives you, since T will fix known value of T, so KT1 is readily obtained. Readily obtained is what? Write the expression A PbO solid, activity of Pb liquid over PO2 power half. I will give you the diagram finally. I am developing the equation, then I will draw the diagram, or I will give you before I end today, before I complete today, I will give a rough sketch, okay? Maybe next day we will draw, okay? We'll draw in a actually nice manner. So I mean, actually, it is okay. I am giving you the figure that will emerge finally. I give you rough sketch, rough. Next day I will give you a better presentation, better illustration. This is the, okay, what you plot, you very well know. PO2 power, PO2 on the y-axis, x-team as I told you. X-team moving from 0 to 1. This will be team 0 means pure lead, pure team. Okay. This is what? This is okay. And this is PO2 is okay. This is okay. Very good. Expression. And temperature is fixed as I told you. T is fixed. Right here, T is fixed. Fixed T is for giving temperature. Temperature I will tell you, I will explain you later today. This temperature we know is fixed, is actually at 1023 Kelvin. 1023 Kelvin. What is this? 750 degree centigrade perhaps, huh? 750 degree centigrade. Okay, PO2. This is what? Lead tin alloy. The alloy, I am sorry, liquid. The liquid phase, which is lead tin. Actually, let me write here. And first of all, let me label this. This value is very important. This is the minimum tin that you can achieve in the softening of lead treatment. This is the answer. Or the diagram is here. Diagram is here. I'll label this. Let me give this value. This value is point. I'll give you for this temperature. I consider the temperature, practical temperature. This one. PO2 will be value I will give you. 2 point. PO2 I am writing here. PO2. So that I will write this value is 2.26 times 10 to the minus 12 atmosphere, and this value is very close to this 2.24 times 10 to the minus 12 atmosphere, and this value is 1.02 into 10 to the minus 19. 1.02 times 10 to the minus 19 atmosphere, this one, and this phase is, now you write, what is the phase? Liquid phase, lead tin alloy. What you will get? here liquid plus tin oxide, let me write this way, liquid, right here, liquid plus tin oxide solid, and what you will get here, here this is actually, I don't have space here, this is liquid plus lead oxide solid, this space, and this will be, top will be lead oxide solid mixture plus tin oxide solid mixture. This is the whole story. This equations. What is our job? Find the equation of this line and find the equation of this line. This is maybe tin curve, this is a lead curve, and where they intersect. That is additional question. And then what is the pressure, etc. And particularly these are the for pure lead and oxygen. This is the pure lead and PbO solid. Delta G0 gives you this value, this value. And if you know this, and this value also similarly, tin, this is the tin, tin liquid, and tin liquid, this is also, I am sorry, this is not lead solid, this is lead liquid plus oxygen goes to lead oxide solid, I am very sorry, this is a liquid phase. This is tin liquid plus oxygen gas goes to SnO2, and delta G0 gives you from equilibrium constant PO2 this value. This value forms 10 delta G0, and using delta G0 is minus R10K. These values very critical, obtained by the solving this curve and this curve, or rather getting the equation of this curve, and where they meet, you can easily meet them. Then you will get this, and more importantly, this value 0.005. This is your answer to the question. Very important question, industrial question. Is this? What is the? Suppose you start with certain alloy. What is the maximum extent of tin removal under this condition, this temperature? Maximum extent, say tin is here this side, tin remove, tin remove towards purer and purer lead, tin remove from lead alloy, remove. This is the maximum. Remove, how it is removed? By blowing oxygen, and tin oxide is separated. And liquid is gradually enriched, progressively enriched with lead. Good, very good. Softening of lead. Remove the impurities from lead, and it will reach. That is the maximum. And that is very small value also. 0.005, that is the limit. We cannot get less value of XSN. Value of XSN less than 0.005. Any smaller value not possible, or purer tin not possible to attain. This is the maximum purity. That is the impurity is 0.005 mole fraction of tin in the lead. That is the possible. For the, as long as this temperature is fixed. Okay. So this is the maximum extent of removal. If you further, if you say I will further blow, increase oxygen, blow, then it will be what happened? Up to this point, tin was being removed preferentially. Tin only, and liquid is getting enriched. So liquid two phase. Liquid is here, tin oxide here. Okay, pure tin oxide. Liquid is enriched since tin is separated. So liquid is progressively enriching lead. And when here, if you further blow with the hope of having even smaller tin, then what will happen? No, lead will start oxidizing, and lead oxide solid will start forming. So you cannot. So your objective is not to oxidize lead. So anyway, this I will actually, maybe I will take up next class also. This I cannot finish. Let me finish this part. So what is the cardinal thing or crucial thing? Get the equation for this curve, and you all set. Get the equations like this, like this, metal curve and oxide curve equations, and the stability diagram is over. So so A plus BT is, I have written here. Now what is this value? Tell me. What is this value? This value is 1. What is activity of lead liquid is what? Tell me. This is actually non-ideal solution, but remember, here lead is at equilibrium. When you have this is actually maximum extent. So tin is removed and small concentration of tin will be at equilibrium. Okay, when tin is removed, when you have actually liquid plus tin oxide, you reach this state.
2 hours complete.
Complete. I'm complete. I'm complete. 1 minute. Stand here. Okay, wait here. And so tin oxide, so it will be almost very small concentration of tin, means large concentration of lead, and at large concentration, you know, Raoult's law, non-ideal solution tends to behave ideally. Recall. At high concentration, suppose this is the Raoult's law. At high concentration, what happens? The deviation, but at high concentration, it merges with the Raoult's law. So activity is mole fraction. Okay, XP will. So this you will write actually. So this next class. Stop here. This I will take up. That activity is mole fraction. I am writing you. Then I will take up. This is nothing but in terms of tin. Since tin is a variable. Babu. Yes. It is 1 minus binary liquid. 1 minus excitation. This part I will take up next class. Next class from here. Next class. Okay. I will start from here. From this and complete this problem. Thank you very much for your patience and for your interest and cooperation. So see you next class. Bye.